And as Pyali mentioned, I would, as a disclaimer, I would like to tell that I have not yet worked yet with the pencil code, and the results I'm going to present today are obtained with Muram and MR work code. So to begin with, let's see how the plasma flows on the solar surface actually looks like. So the figure here I show is the continuum image of a full solar disk when the sun is quiet and has no visible sunspots. So here the solar surface looks very calm and smooth, as you can see. Now, if we zoom on a smaller region and look at it from a different instrument, so this image is taken by Phi instrument on board solar orbiter on 28th May 2020. And this covers 200 by 200 megameter square area of a similar quiet sun region as we saw earlier. But now you can see the granulation pattern, which is basically indicating the movement of hot plasma flows under the visible surface of the sun. Now to see the plasma movement, we select a similar but even smaller quiet sun region covering approximately 19 by 100 square. The movie produced by Decast. So this movie displays the highest resolution observations of the solar surface that is ever taken. And I'm pretty sure that you must have seen it multiple times by now. So this covers a period of 10 minutes, and it basically displays the turbulent boiling plasma gas that covers the entire sun. So these turbulent plasma motions near surface can actually jostle and perturb the magnetic fields which are anchored on the solar surface and excite various MHD wave modes, which can then travel to higher layers of the solar atmosphere and then potentially contribute to the heating of the solar atmosphere. So now, if you just look at the image on the right and focus on the two sub-panels that I have enclosed in a red rectangle here, if you can see my mouse. So they display a magnetogram, which is the magnetic field distribution on the solar surface, and the corresponding coronal intensity image, which maps the high temperature plasma in the solar corona. So by comparing these two, from here we can get clues that coronal heating is somehow linked with the magnetic fields. Or we can say that the structure that we see only in the hotter channels of AIA or onboard SDO, they are linked with the strong magnetic regions on the solar surface. However, the exact mechanism by which this magnetic field facilitates the heating of the solar atmosphere is still unsolved questions in solar physics. Now, the two most probable or the two potential candidates in this direction are magnetic reconnection or heating through waves. And I am personally more biased to the latter mechanism, which is wave-based heating. So I intended to use realistic simulations of a strong magnetic flash region and study which wave modes are actually dominatingly contributing to the heating or the energy transport in the solar atmosphere. So I have used Muram code for these simulations. So Muram code basically solves fully compressible MHD equations and treats the radiative transfer in gray or non-gray solar atmosphere. And the code is able to reproduce granulation and radiation observed at the surface of the sun, as well as the solar convection from granular to supergranular scales. So just for the sake of completeness, here I have mentioned some more technical details about the code implementation, but I would not go into the details and move to the specific setup that I use for my purpose. So I started my investigation with slow magnetoacoustic waves, which are naturally excited in my simulations without using any external wave driver. So the sketch here displays the simulation domain. So the simulation box covers 12 megameter by 12 megameter in the horizontal space and 4 megameter in height, which is such that the top of the box is 2.5 megameter above the surface and 1.5 megameter below the surface. And the grid spacing is 10 kilometers in all the three directions. And I initiated these simulations with a purely hydrodynamic setup and ran it for 2 hours so that it reaches a quasi-stationary state. And then I introduced a vertical magnetic field of 200 Gauss and ran it again for some time so that it simulates the Planck region. And since the aim in this numerical experiment was to study waves, I selected a smaller region with the dimension of 3 megameter by 3 megameter by 3 megameter and saved it for 25 minutes at 1 second cadence. And this was done because it was not feasible to analyze this whole data cube at such high resolution and high cadence due to memory constraint. So this smaller region is shown here in this smaller sketch here. Now I show a movie which is a 3D view of the selected domain with colors representing the vertical component of plasma flows, which is basically VZ. So the blue color shows the upflows, while the green color shows the downflows. So the movie covers 25 minutes of actual solar time, and we can see these periodic enhancements of upflows with periodicity around 5 to 6 minutes that are caused by global P modes due to solar convection. And these structures, if you notice, are very similar to what Shohail presented on Tuesday in his speckle study with pencil code. However, in our case, our objective was to investigate waves. So we had kept the vertical extent of our simulation box only up till transition region. And therefore, we do not actually compare them to speckles. But the physical origin is same. It's basically the P modes, periodic P modes. And one important thing here is to note that these localized flows do not maintain at the same spatial location. They are continuously shaken by the granular motion. Therefore, if we intend to study the waves which are traveling along the magnetic field lines due to these periodic upflows, it is important to track the individual magnetic field lines which are carrying these waves, both in space as well as in time. So before I move to the methods and results, I would like to show some more movies from the simulations in order to give you some idea of the plasma motions and magnetic fields at the solar surface in the simulation I used. So on the left-hand side, we have vertical component of magnetic field vector. And on the right-hand side, we have vertical component of velocity at the mean solar surface. So here we can see that although our field in the simulation is very strong, it's strongly magnetic Planck region, it is continuously evolving. And the magnetic fields are actually moving around, and convection, if we look on the right-hand side, convection is not inhibited even inside these strong magnetic elements, which is actually the case for sunspores, which have similar magnetic field strength, but a larger area coverage. Therefore, to study slow magnetoacoustic waves that travel along the magnetic fields, it was important to track these individual magnetic fluid parcels in space as well as in time. So now I will discuss the magnetic field line tracking method that I used. So this is a map of vertical component of magnetic field strength vector at the mean solar surface at the beginning of the sequence I analyzed. Now, in the middle, I show a subregion which I used for the present study and corresponding to this red color box on the left panel, which is now zoomed in the middle panel. So as I already mentioned that the slow magnetoacoustic waves travel along the magnetic field lines, and it is important to discern the temporal evolution of individual magnetic field lines for studying waves. With this aim, we place some seed points in this magnetically concentrated region at the mean solar surface, which I am displaying as white asterisk in the right panel. And then I follow the field lines which are associated with these asterisks in space and in time. Now the cartoon here actually demonstrates the procedure I used for tracking the field lines in space and time. So let us assume that we have a seed point representing a magnetic field parcel at location A at the mean solar surface at the beginning of the sequence. And now we trace the magnetic field line in 3D domain using the magnetic field vector component at t equal to 0. And then we use the velocity vector at this initial location to calculate the displacement of each seed point by integrating in time. Okay. And in this, we are assuming that the velocity is not changing much in 1 second because we have data at 1 second cadence. Now let's assume that it reached a new location B, which need not necessarily be on one surface. It can be above or it can be below. And then we trace the magnetic field back and we from the new location B, and come to a new seed point, which is the intersection of this field line from the z equal to 0 layer. So now this is important to return back to the solar surface along the field line at each time step, because near surface magnetic field is more or less frozen into the plasma fluid and diffusivity is less. Therefore, following the plasma fluid, we are basically following the magnetic field. And then we continue this procedure for the entire time sequence, which is 25 minutes. And as an example, on the right panel now, I show the trajectory of a magnetic field line corresponding to the seed point, which is shown here in the cyan asterisk. And this actually shows the magnetic field line where it cuts the z equal to 0 plane. And the color of this curve corresponds to the time elapsed since the beginning of the tracking, and axis show the spatial location. So it starts from here, so the field line is continuously moving and ending here after 25 minutes. So, and in this movie, I show the temporal evolution of this field line in 3D space. So the green curve shows the magnetic field line, while the red curve is the vertical line at the initial seed location. And the horizontal plane displays the saturated map of vertical component of magnetic field strength. And we can see that magnetic field line actually is continuously moving. It bends when it is at the edge of the magnetic field concentration, or we can say that magnetic field expands at the edge of the concentration, but it is mostly vertical when it is in the core or in the center of the magnetic field concentration. So after following these individual magnetic field lines for the full time series, we intend to study propagation of slow magnetoacoustic waves along this field line. So for that, we calculate the component of velocity along the magnetic field vector, which is the longitudinal component of velocity at each time step, and constructed a height time map. So this map shown here is for one example case again, which is shown by this cyan asterisk. So the background here clearly maps or indicates the forward propagation of longitudinal velocity perturbations along the magnetic field lines. For comparison, I have overplotted the paths of test particles moving with local sound speed, which are displayed by these solid black lines. And around 1 megameter, you can see that propagating slow waves actually convert into shocks, or they actually shock and travel faster than the local sound speed at those locations. And for comparison, in the bottom panel, I have also displayed here a space-time map for the vertical component of velocity at the initial location of the selected seed point. And because as it would be observed, if we are not tracking the field line in time and we are just observing the vertical component at a fixed location, as we can do in the direct observations. So here we find that the map is not at all smooth in this case. And the reason for these intermittent fluctuations is that the waves that are traveling in the neighboring field lines are not in phase even when they are in the same magnetic element, which shows the importance of tracking these field lines to correctly or to precisely analyze the wave properties. And after that, I performed wavelet analysis to see the dominating wave period of these waves at different heights, and took the average of all the spectra corresponding to the seed points, which I displayed earlier with white asterisk. So here we see that with height, for example, this is z equal to 0, 500 kilometer, 1000 kilometer, and 1500 kilometer above the surface. So we can see that with height, the peak wave period is shifting to lower wave periods. And this is due to the acoustic cutoff, which basically doesn't allow low frequency waves to propagate. And this averaging is because it only includes the field lines which were mostly vertical, and therefore they stayed in the selected region for the entire sequence. But it has been previously shown in observations that low frequency waves can actually lead to higher layers along the inclined magnetic field lines at the edges of strong magnetic elements in plush. Now, to test that wave leakage in our simulations, we computed wavelet spectra, which is averaged over the whole horizontal domain, not only in the magnetic concentrated region, but the whole horizontal domain. So different panels here correspond to different heights above the main surface, which I mentioned in each panel here, as you can see, 1500 kilometer, 500, 1000, and 250 kilometer. The black curve shows the power spectra that is calculated using longitudinal velocity, which is along the magnetic field vector. Red curve shows the power spectra using the vertical velocity, VZ component. And also, like, we are using spatial resolution or the grid spacing of 10 kilometers, which is not yet achievable with the solar observations. So we also degrade our simulation data for 100 and 200 kilometer resolution, and again calculate this horizontally average power spectra for vertical velocity. And we found that all the curves, most power in lower solar atmosphere is peak around 2.5 millihertz, whereas in higher layers, there's more power around 4.5 millihertz. This shift is again due to the acoustic cutoff. But if we compare black and red curves, we see that there is more power in the longitudinal velocity than the vertical velocity, which is again expected because slow waves actually propagate along the field lines, not in the vertical direction. However, in the upper layers where the field is more or less vertical, we see there is not much difference in black and red curve. However, if we compare red curves with green and blue curves, which are calculated using the degraded data, we see that power is reduced due to smoothing. And this reduction in power is more in high frequency waves. Means the reduction in power, if we compare red and green and blue curve, is more in high frequency waves than in the low frequency waves, which indicates that high frequency waves are actually associated with smaller spatial scales, and therefore they are more severely affected due to the spatial resolution. And this also indicates that it could be that waves, these high frequency waves are generated by turbulence, and therefore high frequency waves are associated with smaller scales, and then they will be more affected by the degrading procedure. Next, to investigate the energy contribution of slow magnetoacoustic waves, we calculate acoustic energy flux using the velocity power spectra, using the relationship which I mentioned here. And we find that we find higher energy flux when using parallel component of velocity component compared to the vertical component, which is shown in the red color. But they are two very similar in the chromosphere because magnetic field lines are more or less vertical of the in Planck region. And not so surprisingly, if we degrade the resolution, our wave energy flux is reduced by a factor of 2 or 3 in these two resolutions that I've tested here. And the height range from 5 to 800 kilometers actually falls in low chromosphere, and the energy flux available at 800 kilometers above the surface is approximately 10⁴ watt per meter square, which is actually sufficient to balance the estimated radiative losses in the layers above this height. So basically in this work, we developed a field line tracking method to track individual magnetic field lines, both in space and time, which are continuously advected and jostled by the plasma flows at the solar surface. And we found that acoustic wave energy flux due to these waves is actually sufficient to account for the radiative losses in the chromospheric region of Planck. So now I come to the second part of my talk. So until now we have talked about slow magnetism because it is comparatively easier to separate out the plasma motion due to slow waves, especially in simulations where we have vector magnetic field information in the whole simulation domain. And moreover, since slow magnetoacoustic waves are of compressive nature, they have density perturbation, and therefore it is also easier to detect them in direct solar observations. While if we talk about the transverse wave, for example, fast magnetoacoustic waves or Alfvén waves, which have oscillations in the plane that is normal to the background magnetic field, their isolation is non-trivial because there are infinite number of vectors normal to a given vector. Moreover, they both are of Alfvénic nature, so they don't have density perturbations, which makes them very difficult to detect from the direct solar observations. However, it is really important to separate out these contributions from transverse waves so that the heating processes that we observe in simulations or in observation, that can be independently associated with the different wave modes. So in literature, there are several analytical expressions available which can separate out these three MHD wave modes, but they are usually derived under certain approximations, such as considering one axis as invariant directions or considering some symmetry around vertical direction. But there are no general methods which can be applied to, let's say, complex 3D magnetic configuration that might be resulting from numerical simulations or from magnetic field extrapolations. And since I wish to study MHD waves in my simulations, so I developed a new wave decomposition approach, which relies on geometry of individual magnetic field lines to isolate the three fundamental MHD. However, to validate this method, I couldn't use the numerical simulations. I had to choose a setup which has an axis of symmetry, so that for example, the flux surface method that was put forward by Mumford et al. In 2015 can be used, and we can compare our result with their method to get confidence in our approach. So to compare these two methods of wave decomposition, we performed ideal MHD simulations using an open source Ampere MR work code, and we simulated a magnetic null configuration setup extending from solar surface to solar corona, as I have shown in top left panel. And then we applied a rotational driver at the bottom boundary, here at a localized region. And that driver I am showing here in the bottom left panel. And the top right panel displays the stratification of the atmosphere from photosphere to the solar corona. And the magnetic field configuration is of a null point. And here I am constructing a few constant flux surfaces shown here in the bottom right panel, and applied the two methods to compare the results in order to validate our new approach to separate the wave modes. So now the cartoon on the left, this one displays the flux surface method that is put forward by Mumford et al. In 2015. So in their method, slow magnetoacoustic waves is again along the magnetic field vector. But to get the direction vector for the other two components, they constructed a numerical plane by joining the adjoining or the consecutive magnetic field lines in this axis symmetric flux tube. And then they computed the vector which is normal to this plane and associated it with the fast wave. And then the third vector of this orthogonal system is associated with alpha wave. However, this method can only be used when there is an axis of symmetry. For example, for example, in the simulations, when we have a magnetic field or a flux tube, it need not to be always symmetric. So in that case, we cannot apply this method. To overcome that limitations, we propose a new wave identification method, which is based on individual magnetic field line geometry, and that can be uniquely defined in any complex system. And that is shown here in this right cartoon. So slow magnetoacoustic wave is again in the same direction, in the direction of magnetic field vector. But for the other two waves, we constructed a plane by joining the three consecutive points at magnetic field line, at each magnetic field line. And then the vector that is normal to this plane will be associated with alpha wave, because this is normal to the plane in which magnetic field is lying. And the third vector of this orthogonal system will correspond to the fast magnetoacoustic wave. So here I show the three selected surfaces which I took out from my magnetic field configuration. And the next two rows, these two rows display the alpha component of velocity vector, and the bottom two rows displays the fast component of velocity vector. So our result with this new method, which are shown here in the third row and the fifth row, matches pretty well with the approach that is used by Mumford et al., which is shown here in the second and fourth row. So that gives us confidence in our new approach. But the thing is that both the method gives identical results, which we expected in this symmetric setting. However, the proposed method has advantages over the flux surface method, because now this can be applied to more realistic scenarios where the magnetic field configuration does not have to have an axis of symmetry, for example, which is resulting from field extrapolation of realistic simulations. So currently I'm using this method and comparing the wave propagation and interaction with null, both with the vertical driver and rotational driver. And this movie actually shows the evolution of velocity components associated with the three components of velocity, slow, alpine, and fast, by applying rotational or the vertex driver or the vertical driver. So the key takeaway here is that the fast wave, which are known to accumulate at the null point and drive energetic jets, are more pronounced with vertical driving, as you can see here in this panel. And that is possibly due to the at the alpha acoustic equipartition layer near the null point. So now my next plan is to use this method in my realistic simulations of BLAST and to investigate the propagation of fast and alpine waves and their role in energetics in the solar atmosphere. So to summarize, we propose a new wave decomposition method, which can be applied to realistic scenarios where the mandatory configuration need not to have an excess of symmetry. For example, field resulting from field extrapolations or from realistic simulations. So I will stop here and take your comments and questions, if any, and thanks for listening.
Yeah, thank you, Nitin. That was a wonderful talk. And I'll just check if there are raised hands.
Sure.
Questions. Axel has a question. Axel, can you unmute yourself?
Yes, thank you very much. That's very interesting science that you are doing. I was wondering about the 11 species that you are considering for your ionization in the first part of your talk. What are all those? I mean, when we are doing simulations, first of all, we don't have necessarily the ambition to do it highly realistic, but reasonably well still. And so what we only use is neutral hydrogen, ionized hydrogen, and neutral helium. That's sort of the minimum. Relative to that, when you have additional species, you probably have helium ionization states 1 and 2. That gives 5. Do you also have metals somehow, and then which would be 6? But how do you then in the end get 11?
I don't know which all species are actually accounted for. I don't remember, but they are basically the species which are observed in mostly main components in photosphere and chromosphere, and their ionized levels. And they are used to calculate the equation of state, because we are not using the ideal equation of state, but we are using the calculated tables, which are basically coming from these ionized species. So I don't remember which all are included. I think calcium also, till calcium 1, calcium 2, but I don't remember which all species.
Okay, I see. Yeah, then you sort of don't even care how many they are because it's just a table. Yeah.
Yes,
right.
it is used to calculate the table.
Yeah. Okay.
Okay, so this table is for the equation of state, is it? Or...
Yes, right. So at each time step, we need a relationship between the thermodynamic quantities. So that instead of using a relationship like ideal gas law, we use these tables.
Yes. Yeah, just for clarification, for the others, maybe, I mean, one might think that it's always better to use a table because then it's as realistic as it gets. But there is a certain interest in really modifying physics, actually, to really understand what's going on. If somebody now asks, for example, how important is the helium-2 ionization, and if it is simply not a table, but if it's simply a parameter that you can change during one time and other situations, you have an additional degree of freedom. So I just want to add this for clarification to those who may wonder why we do a thing like this, that we actually calculate things only. So for example, for the opacity, that we know that when you actually do a direct numerical simulation, it becomes extremely hard to really do that. And the only way to do a direct numerical simulation means that one actually does not use an LES, a large eddy simulation. So we actually use the actual diffusion operators as they are. And then it's impossible to do a real radiation transfer simulation with a realistic opacity. So what you then can do is you can scale the opacity and simply make the opacity smaller by several orders of magnitude. And then eventually it actually works. And by that moment, one only realizes how much numerical physics actually goes into the actual calculation. This is many orders of magnitude actually, and at least that's my personal concern, that I would like to understand exactly how important that is. So, for example, in reality, the layer of the sun is over which the ionization happens is extremely thin. I mean, this is maybe even less than 10 kilometers thick or something like that. It's extremely thin on global scales. Anyway, that was just my personal comment here on these things. But thank you very much for the presentation.
So, Nitin, I have a small question about the tracing of the field lines that you have done. So, so the seed points that you showed at the bottom boundary. So, are you only following those seed points and then tracing the field lines, or initially you take several points on a single field line and then track how those points are moving? So, I mean, are you tracking a single field line, or are you tracking the seed points only?
Okay, so I will explain it a bit more detail. So I put initially around 100 seed points at the solar surface. And then those 100 seed points I traced in time with the method that I explained here. Like at each point, I go to the next point, come back to z equal to 0 level, go to next point, come back to z equal to 0 level. But what happens is, since the domain is limited and the field lines expand in height, so many times it happens that the field line is going out of my domain. So I had to discard those data sets which were not continuous in 25 minutes. So at the end, I was only left with 25 seed points, which I was tracking in height and in time, but they stayed in my selected region. So then I took average over those field lines to see what happens when when I'm actually tracking the field lines instead of looking at one place.
Okay.
So these different seed points are not on single field line, but they are spatially distributed on the surface.
So you don't take several points on a single field line and follow them. You are not doing that.
No.
Okay, thanks, Nitin. Very nice presentation, and thanks a lot for joining us.
Thank you very much for listening and giving me a chance to present non-pencil work.
No, we would